All right, let's dive in. Today, we're going way beyond the basics, into one of the most powerful and complex stories our planet has to tell, the ongoing saga of the Himalayas. It's this incredible story of creation, of destruction, and of a geological engine that literally reshaped our world.
Now that sounds like a total paradox, right? But it is the absolute truth when it comes to the Himalayas. And this one idea perfectly captures the epic battle we're going to talk about, this clash between colossal uplift and just immense erosion. That dynamic tension, that's what defines this mountain range, and it's really at the heart of our deep dive today.
Okay, just a quick heads up before we get rolling. We're jumping straight into the deep end here. We're going to be getting into some pretty advanced geological concepts. So if you're looking for more of a 101, a foundational overview, we've totally got you covered. Just check out our previous explainer on this topic.
So here's our game plan. Think of it as a grand planetary cycle. We'll start with that initial massive tectonic collision. Then we'll get into the nitty-gritty mechanics of how you actually build mountains like this. From there, we'll see how it rewrote the global climate, look at that constant battle between its rise and fall, and then, and this is the really cool part, we'll see how its own destruction is literally seeding the continents of the future.
All right, let's kick things off. Our story starts with what is, without a doubt, the single most powerful geological event of the last 50 million years. We're talking about a collision so immense, it would literally move mountains and completely wipe an entire ocean off the map.
To really get your head around the scale of this, you've got to look at this timeline. For millions and millions of years, the Indian plate was just racing north. And when I say racing, I mean it, at speeds up to almost 20 centimeters per year. In geological terms, that is absolutely flying. It covered 6,400 kilometers before that inevitable, world-shattering collision with Asia.
So what was in the way? What stood between these two colossal continents? Well, it was an entire ocean, the Tethys Sea. And what this means is that the birthplace of the Himalayas wasn't even land. It was the ocean floor. That's the key. It's exactly why, to this day, you can find marine ammonite fossils at the summit of Mount Everest. That ancient seabed got squeezed and shoved 8 kilometers straight up into the sky. Wild, right? Now, it's really important to picture the scene right before the big collision. The geology was totally different. You had the Tethys Ocean floor sinking or subducting under Asia. And as it sank, it melted, feeding this huge chain of volcanoes all along the edge of the continent. If you want a modern-day picture, just think of the Andes in South America. That's what it looked like. This was the world right before everything was about to change forever. Okay, so how on earth does a collision like this actually build the world's highest mountains? Now, you've probably heard the simple explanation that the crust just folded. Well, I'm here to tell you that's not just an oversimplification, it's basically wrong. The real mechanics are way more complex and frankly a lot more violent. So here's the thing, and this is absolutely key. You can't just fold thick continental crust to build mountains this high. It just doesn't work that way. The plates had to somehow absorb thousands of kilometers of convergence. So the solution wasn't folding. It was a process called crustal shortening. And what that means is the crust literally had to break and then stack on top of itself. And this shortening happened along a series of enormous fractures in the rock, which geologists call thrust faults. The best way to picture it is to imagine pushing a deck of cards from one end. See? They don't fold, right? They slide up and over one another. That is exactly what happened here, but on a mind-boggling continental scale. Massive slabs of rock were thrust upwards and southwards, one after the other, in this very specific order.
And what was the end result of all this? Well, all that stacking created what geologists call a duplex structure. And what it did was it basically doubled the thickness of the continental crust, from a normal 35 or 40 kilometers to an absolutely immense 75 kilometers. And it's that incredible thickness, that deep root, that's able to support the highest plateau and mountains on the entire planet.
But wait a second. This brings up a really critical question, doesn't it? I mean, in most tectonic collisions, one plate dives or subducts under the other one. So why was this one so different? Why did everything go up instead of one plate going down? The answer, in one word, is buoyancy. See, unlike dense oceanic crust, continental crust is just too light. It's not dense enough to sink back down into the mantle. So when India and Asia collided, neither one was going to give way. It was like smashing two giant styrofoam blocks together. There was nowhere to go but up. And as a little side note, this is also why those Andean-style volcanoes we talked about in Tibet went extinct. The subducting oceanic plate that was feeding them with magma, well, it got shut off. Okay, so this collision was obviously a continent shaper.
But its effects were much, much bigger than that. This event fundamentally re-engineered our planet's entire climate system, and its consequences are things we are still feeling every single day.
Just take a look at this comparison. It's amazing. Before the uplift, you see the high-altitude jet stream flowing in a relatively smooth, straight path. But then, as the Tibetan Plateau rose up, reaching an average height of 5 kilometers, it created this massive wall in the atmosphere. And that physical barrier literally forced the jet stream into these huge, meandering waves all across the northern hemisphere.
And those huge waves in the jet stream, they had some truly profound effects. For one, a leading theory suggests that they helped steer frigid Arctic air way further south, which may have helped kickstart the ice ages. At the same time, that high plateau became a gigantic heat pump during the summer, which dramatically supercharged the Asian monsoon system. And of course, it created one of the world's most dramatic rain shadows, giving us the arid desert of Tibet to the north and the incredibly lush, river-fed plains of India to the south.
So, let's circle back now to that central paradox we started with, this epic, non-stop battle between the forces pushing the Himalayas up and the relentless forces trying to tear them right back down.
And make no mistake about it, this is not ancient history. The tectonic collision is still happening right now. India is still pushing into Asia, and as a result, the Himalayas are actively rising by about 5 millimeters every single year. I mean, think about that. That's half a meter every century.
But here comes the counterforce. Gravity and water are just absolutely relentless. You've got these incredibly powerful monsoon rains and glaciers just chewing away at the rock. And get this, the Ganges River, just by itself, carries over 500 million tons of mountain out to sea every single year.
So this sets up the ultimate geological puzzle, right? You've got these two colossal opposing forces, uplift and erosion, and they're happening at roughly the same rate. So what's the deal? Are the mountains actually growing? Are they shrinking? Are they just stuck in some kind of really volatile tie? And look, this isn't just some abstract, theoretical question for geologists. This dynamic balance has very real-world consequences. It makes the Himalayas one of the most hazardous regions on the entire planet. The constant uplift builds up stress that eventually gets released in these devastating earthquakes. And at the same time, all that erosion triggers catastrophic landslides that can literally reshape an entire valley in the blink of an eye. But that begs the question, what happens to all that mountain that gets worn away? All those billions of tons of rock and sand, they don't just disappear. Well, now we're going to follow that sediment on its incredible journey, a journey that actually completes a planetary-scale cycle of renewal.
Let's just follow the story of a single grain of sand. Imagine it. It starts its life by being scraped off a Himalayan peak by a glacier. Then it gets carried down a river, maybe through the world's deepest gorge. Eventually, it settles in the massive Ganges Delta, before getting swept out into the Indian Ocean. But its story isn't over, not by a long shot. It gets carried thousands of kilometers away to the Indonesian subduction zone. There, it's pulled back down deep into the Earth's mantle, it's melted, and then, unbelievably, it's erupted back onto the surface from a volcano, creating entirely new land.
I mean, how cool is that? It is the ultimate geological recycling program. The very same material that once formed the roof of the world is being systematically broken down and reused. It becomes the raw material for building new continental crust in places like Indonesia. It's literally fueling the tectonic engine that will, over hundreds of millions of years, build our planet's next supercontinent. Wow, okay, that was a lot to take in. So after that deep dive, let's try to boil it all down to 5 key takeaways. Okay, number 1. The Himalayas didn't form by simple folding. The crust had to break, shorten, and stack on top of itself because those two continents were just too light to sink. 2. This massive uplift completely rewired the planet's climate, influencing everything from the ice ages to the Asian monsoon. 3. The mountains are locked in this incredible paradox, this dynamic balance between rising up and being torn down. 4. This isn't a static landmark. The Himalayas are a living, breathing, and often very dangerous, active geological process. And finally, number 5. This whole epic story is part of a grand planetary recycling system, where the destruction of old mountains provides the raw material for new continents. So, we've seen how this incredible tectonic engine works from that initial collision all the way through to recycling, and we know the process is still running. So that leaves us with one final fascinating question to ponder. If we look at our planet today, where is this engine going to build the next Himalayas?